So this lecture is going to be a supplementary lecture for rigid dynamics and subsequently for its actual course, which is Catboy gravity. And today I'm going to talk about actions. So what exactly is an action?
I don't know if you guys can see the board. Let me just lower the brightness down.
Okay, so actions. What are actions and why do we want to study them? And why are they important in studying the geometric dynamics of my catboys? Now, when we talk about a system, a physical system, whether it be a particle or set particles or an astronomical body or whatever, we are concerned primarily with its energy, namely the kinetic energy and the potential energy. You know what the kinetic energy already is. So in the Newtonian formalism of physics, we know that the kinetic energy is simply 1/2 times the mass times the velocity squared. Now the kinetic energy is different, namely that we're talking about a rest mass, and then we multiply by a certain gamma depending on how close we're to the speed of light. So gamma times 1/2 the rest mass of the particle times the norm of the forward velocity squared. Right? So V alpha squared, where V alpha is simply the derivative with respect to the lambda of my position vector x alpha, which is also a function of lambda, supposedly, for a parametrization of lambda. So that is for this one's for the Newtonian formalism, and this is for the relativistic formalism. And for the potential energy that is given in various forms in quantum mechanics is the potential function big phi of xt. In the Newtonian formalism for a one-dimensional system raised at height h, it is simply the mass times gravity times the height. So this is for quantum mechanics. And this is for the Newtonian and one-dimensional. So that's kinetic energy, potential energy, and of course we also have the total energy, also known as the Hamiltonian. And we'll get into Hamiltonian physics in a future video. And you guys will know the Hamiltonian from rigid dynamics. Namely, it is the sum of the kinetic energy and the potential energy. We studied this in the form of the left-hand side of the Schrödinger equation. Negative h bar squared over 2m times the Laplacian squared of my wave function plus the potential energy phi xt is equal to the energy, which is energy of the wave function, which is I h bar d by dt of the wave function. So this left-hand side is the Hamiltonian operator on the given wave function side. So that's one example of the Hamiltonian. Now, another thing that I want to discuss that leads up to the action is something called the Lagrangian. So what is the Lagrangian? Because the upshot of this lecture is that as soon as you know what the action is for a certain particle, you have essentially every bit of information you need to know about that particle, especially when it comes to its movement through spacetime or through an arbitrary spacetime. So, what exactly is an action? An action is some scalar quantity or a function which is simply the integral of the Lagrangian with respect to some parameter. I'll call it dmu. Or along where dmu is some parameter along the world line of my particle. So the Lagrangian is then equal to the kinetic rest mass times the norm of my forward velocity squared. And the potential energy is something else. It's going to be some scalar field or whatever. So I'll just call it small phi. So the Lagrangian would be this minus this in Minkowski spacetime. So that depends on what the conditions are for your particle. It could be zero or whatever. But the most basic one, of course, is that the Lagrangian is equal to the kinetic energy of the particle, which is if it has no potential energy essentially, and it's moving, right? If it's moving, it must have zero potential energy and only the kinetic energy. So that's 1/2 the rest mass. So gamma times 1/2 times the rest mass times the norm of my forward velocity squared. So taking the integral of this over here with respect to the parametrization of my v or my velocity here, or velocity alpha, of course, is equal to the derivative of my x alpha with respect to my d lambda, so that my action, if my Lagrangian is equal to my kinetic energy, is an integral of gamma times 1/2 the rest mass times the norm of velocity squared d lambda. So this one here is my action. Now, gamma and 1/2 and the rest mass are, these guys are constant, so you can pull them out whatsoever. So then my action for Minkowski spacetime for a certain particle with rest mass m, supposing it has potential energy 0, is then gamma times the rest mass over 2 times the integral of the norm of the forward velocity squared with respect to my property or my parametrization alpha. Alpha could be tau, which is the proper time. So if I want to actually find the action between 2 points, then I will be integrating and then taking limits along the world line of the particle. So if I have a certain particle traveling through a world line, I have a certain tau2 and a certain tau1, and I want to find the action along this curve, I simply integrate the Lagrangian ranging from tau1 to tau2 with respect to tau. Okay. So that's the action. Now, let's get into the general form of the action for a massless particle. Now, things are much different when we consider an arbitrary metric tensor, g mu. So now, again, like every lecture concerning g mu, consider g mu an arbitrary metric tensor that determines the spacetime around a given Catboy, and so once we have our spacetime, I send a test particle of a certain mass m through the spacetime. So what is then the action s? So this time we are considering still the parametrization. However, we're now considering an arbitrary metric tensor rather than just the Minkowskian metric. So then, for a mass or massless particle, so the problem with the last equation is that if I consider, say, a photon traveling through the system, well, it's going to break the equation. It's going to give me an action of 0, despite photons having non-zero actions, because they act like any other particle and interact with the world like any other particle. So the action must not be 0. But the thing is, the mass of a photon is 0. So there's a problem there. Now, this is where I'm gonna write this equation. You guys are gonna use that for future exercises and future reference. So, maybe now the action for a certain particle of mass m. So, the action for a mass less or massive particle so this mass would be denoted m, is then still the same thing, but you're integrating with a different variable psi, which is an arbitrary one. So it would then be negative 1/2 times the integral of, with respect to psi, of my sigma times psi times dx over d psi squared plus m squared over sigma of psi. Where this psi over here, this sigma of psi, is a scalar field called the Einstein field. And it makes sure that when we translate the action, so if I have some curve over here that my particle travels along, and I translate it somewhere without stretching or doing anything to it, the Einstein field ensures that the action stays the same. So it's a scalar field that ensures that no matter where I transport, or no matter where I translate or rotate or whatever my world lies, so long as I don't change it fundamentally, the action along that path or that world line stays the same. So it's the same quantity. That's what the Einstein field ensures. So a little note on the notation. So this dx by d psi squared is the norm of my x, my position along the world line. This is my g mu nu contracted with my dx mu by d psi times dx nu by d psi. So this is a small notational thing. So I define this symbol by this relation. So you guys will think that, okay, yeah, there's my arbitrary metric tensor. So the full expanded form that you need to consider is that this. So S is negative 1/2 times the integral by d psi of my Einstein field sigma times g mu nu times dx mu by d psi dx nu by d psi plus my mass squared over sigma of psi. So this is the full expanded action of my particle. And we need to consider every index mu and nu. But really it's just a contracted form of my dx by d, or contraction of my x with the metric tensor essentially. So from this action, we can extract a couple of equations of motion for our given particle. So just input the mass, and you essentially get the action for the particle. So for a photon, this term would cancel out. So for a photon, because the photon has a mass 0. So if I'm going to consider a photon, which is the most basic, almost the most basic of them all, because it has a 0 mass, then my equation changes to something much more simple. So I don't need to consider that Einstein field at the denominator that divides the mass, the square of mass. I only have to consider that first term, right, in the integral. So for a photon, we only consider the following equations, or following equation. So the action is negative 1/2, so negative 1/2 stays at the front, times d by d psi of the Einstein field times my dx by d psi squared. So I only need to consider this one here. And remember, recall that for every particle, it follows the least action principle. So S is always minimized. So we always take the limit as get that the equation of motion becomes something like d by d psi times the Einstein field times g mu nu dx mu by d psi is equal to 0. So, that's one thing. Now, the Einstein field satisfies a certain equation. It must satisfy a certain equation. And that is, or no, actually, because we're considering a fluid, that means that it travels along a null geodesic. And because it travels along a null geodesic, it must hold that dx by d d psi, the square of that must equal 0, because we are considering a null geodesic. This and this must be satisfied for my metric tensor, Einstein field, and my position along the world line x mu for photon atoms, right? So now I want to make this equation in terms of lambda, which is my parametrization. So I want to consider a certain type of parametrization that eliminates this Einstein field over here. So in order to do that, what I want to do is define another derivative. I want to define another derivative, and that derivative is that the d lambda by d psi is precisely equal to the Einstein field. By this parametrization, we can do some rearranging, and then we can sort of simplify things further. So I'm just going to write it up here. So the action is -1/2 times the integral with respect to psi of the Einstein field times g mu dx mu by d psi times dx mu by d psi. So that's it. I'm just going to write it here on top for reference. So what I want to do is write this action in terms of lambda. So we look at this relation over here. So rearranging, we get that d psi is equal to d lambda divided by the Einstein field. Right? Makes sense, right? So, and the Einstein field itself is d lambda by d psi. So if I replace d psi with d lambda by sigma, it cancels out with this sigma over here. And then I simply replace my psi over here with this d lambda by d psi. So in total, from this equation, we get something like this. So the action is then -1/2 times the integral along by the lambda of the Einstein field squared. So this time it's different. It's squared now. But it's still somehow the Einstein field is still there. But what's important is that we have made this equation in terms of lambda. So lambda squared times g mu of dx mu by d lambda times dx mu by d lambda. So that is my final equation that I want to derive. So this Einstein field would still be the einbein. It would still correct for translations along space-time of our world line, so that this action stays invariant, essentially. So there's that. Now let's consider G mu nu for Schwarzschild spacetime or Schwarzschild Catboy. So recall that the Schwarzschild metric is essentially the metric or the tensor with diagonal components 1 minus rs over r, negative 1 minus rs over r, 1 minus rs over r, all raised to negative 1, r squared, and r squared sine squared theta. So if I want to consider this, I would contract a certain x mu nu with each of these guys, sum them, and then multiply by essentially this over here. So that would be, so if my x mu of lambda would be some collection or tuple of functions of lambda, namely x0, x1, x2, and x3, then my action for a particle, for a photon traveling through my Schwarzschild spacetime would then be negative 1/2 x integral lambda einbein squared times, so the first term would be this over here, so negative 1 minus rs over r times x0 squared. So that's my first term. So the einbein would still be multiplied to all of them, so I'm going to put another bracket over here, plus my next term over here, so 1 minus rs over r, the negative 1 times my x1 squared. So we're talking about the norm, right? The norm of this, or the magnitude, roughly speaking. So, but it's still a function of lambda, right? So it would still be some sort of lambda forward. So yeah, I don't need to write it down because we know that. So plus r squared of x2 squared plus r squared sine squared theta of x3 squared. So let's close the and then close bracket. So this over here is the full action of a particle, of a photon. So full action of a photon along my G mu or my Schwarzschild spacetime. So each of these is still a function of lambda, so x alpha is still a function of lambda, so still some function of lambda. However, they will be integrated, they will all be integrated and multiplied by the einbein sigma squared. So when you integrate these things, rs over r remains constant. This r squared sine squared theta remains constant. The einbein remains constant because lambda doesn't fully really depend on my einbein. So there's that. This is the action over here. Now for a massive particle, we simply have to add my. So recall that for massive particle, there's a second corrected term in the action m squared over the einbein. And since the einbein is equal to this over here, it would become something like a 1 over is equal to d psi by d lambda. But I don't think that would really work because we're only really doing this for this kind of thing. So if we're talking about a massive particle, we cannot use the parameterization I used over here because we would still have that d psi. So that's it. For Schwarzschild, so we really just have to contract my given position function x with the metric tensor and multiply that by the square of the einbein field. and that's my action. And integrate it all, multiply by the 1/2, I get my action. And of course, again, if I have some world line traveling through space-time, traveling through this certain space-time over here, then I just consider it, and I consider the translation symmetries to construct the Einstein field, and then do whatever computation I need to do over here to find the action. And we always integrate with respect to the parameter lambda, which can be the proper time in certain cases, or most cases. So, the equations of motion a while ago that I showed you guys would transform into the following for Schwarzschild spacetime. So the first one would be d by d lambda of sigma squared times negative sigma squared 1 minus rs over r dx naught by d lambda is equal to 0. And then d by is my first equation, so the first equation of motion that my dx0 must satisfy. Next is d by d lambda of sigma squared 1 minus rs over r, the negative 1 dx 1 by d lambda is equal to 0 as well. So it's 2. So essentially we're doing this, but we're essentially taking the derivative again with respect to lambda and equating it to 0. And you guys will kind of derive or work out that this still comes down to the geodesic equation. Next is 3, so that's sigma squared r squared dx2 by d lambda equal to 0. And then d by d lambda, that's sigma squared r squared sine squared theta by dx cubed by d lambda is equal to 0. It's my fourth equation. So again, you guys can derive this, or you guys can study this and then come to the conclusion that it all comes down back to the geodesic equation. So again, this one over here is my equation for the geodesic. For a photon, right? Considering this case over here, right? So that's really it for this lecture. If you guys want to go further, again, you guys can complete the RS over here for Sir Catboy, 2gm over c to the 4th, or c squared, where m is the mass of Catboy. And then r over here is the radius of the world sphere of my Catboy. The radius of the world sphere. Or rather, the r coordinate, right? The r coordinate, and then there's that. So this one over here is my Schwarzschild radius of the Catboy. So there's that. Right? So if we want to consider the world light along the Catboy itself, so a photon traveling along the world sphere of my Catboy, then we just simply substitute r for the height of the Catboy, because recall that the world sphere is essentially the sphere generated by the height by considering r in the equation x squared plus y squared equals r squared. So r